Our next question is regarding the asymmetric effect and electrophoretic effect. Actually, this comes from the theory of ionic atmosphere. Students should be very familiar with the theory of ionic atmosphere to score good level marks, especially in the CUT PG and also in the JAM, because that is the center of many concepts in electrochemistry. The theory of ionic atmosphere says that if there is a positive central ion, it will be surrounded by negatively charged ions, a bunch of negatively charged ions. Even though I have written so many negative charges here, the theory of ionic atmosphere says to maintain the electron neutrality principle, the total charge should be equal to 0. So if I sum the positive ions and negative ions, it should be equal to 0, meaning to say these negative ions are actually partial negative charges, delta minus. Then only it will add. So it will be equal to plus 1 plus minus delta minus, all those delta minus will add to minus charge. So this will be equal to plus 1 and all those minus charges will be added up, so that will be equal to 0. That is the theory of ionic atmosphere. Now coming to our context, what is asymmetric effect? Asymmetric effect is the time delay whenever I am charging and discharging this one. So see, normally under an electric field, without an electric field, it will be a perfectly symmetric, like a sphere. All these negative ions will be having a sphere like arrangement. So once you apply a negative, or I keep a negative electrode here, these positive ions will start moving from here, and so there is a time delay for this negatively charged ions to go along with the positive ion. That effect is called as the asymmetric effect. And if that is the asymmetric effect, whenever I am applying a electric field, high electric field of 10 to the power of 5, what will happen is this positive ion will move very fast through this ionic atmosphere, since the electric field is very high. So in effect, these ions will not have that time to rearrange and go along with the positive ion. So once I apply a high electric field in the order of 10 to the power of 5 volts, there in effect there is no ionic atmosphere and the conductance will be very high. Conductance will be very high. Now let us check the options one by one. The asymmetric effect disappears, so that is a right option in very high electric field. Now what is electrophoretic effect? Electrophoretic effect is little bit different. Electrophoretic effect is the effect of the, mainly it is the effect of the solvent present in it. So this positively charged central ion and the negative, along with the negatively charged ions, it is called as the ionic atmosphere. It is moving through the solution. So it is, whenever it is moving through the solution, you see there will be a viscous drag. Not only that, if the positive ion and the ionic atmosphere is moving in that direction, there will be a negative ion surrounded by positive ions, positive ionic atmosphere. It will be moving in the opposite direction. So this ionic atmosphere is moving through a flux of the solutions of the ionic atmosphere of the oppositely charged and of the also the molecules of the solution. So there will be a viscous drag. That effect is called as electrophoretic effect. And see, whenever you apply a high electric field, it is not going to make any change in the solution. So electrophoretic effect will always be there. So electrophoretic effect disappears. It is not a correct answer. That is not right. Now option C, the ion moves so rapidly that it loses its ionic atmosphere. That is what I told. Whenever you apply very high potential in the 10 to the power of 5 volts, the positive ion will be moving very fast as if there is no ionic atmosphere. So this is a right option. Now the last one, the weak electrolyte is completely ionized at all dilution. See, it is a very unambiguous one, because the weak electrolyte is completely weak electrolyte, like acetic acid HAC will not be electrolyzed, will not be ionized at all dilution. We know it will be ionized only at very high dilution. So that is the theory of the weak acids. It will be ionized completely only at very high dilution. So that is not partly correct. So this is also not correct. So your right options are A and C. Now I will show a graph in which the increase of the electrical conductance with potential gradient. So you see here I am increasing the potential gradient, and as the concentration increases, this value, the change in the conductance value increases. And also for the valency also there will be a change in the valency. And see, actually for the last option, at very high, even high, not to the 10 to the power of 5, if you go to the potential of 10 to the power of 8, the weak electrolyte will be completely dissociated. But since here we have given only an electric field of 10 to the power of, and that effect is called a second Wien effect. So just remind, there may be a question from that one also. Second Wien effect. What is second Wien effect? If you increase the potential greater than in the order of 10 to the power of 8, so much higher than 10 to the power of 5, at that effect the weak electrolytes like HAC will be completely dissociated into H plus plus AC minus. There will not be a back shift. That is only at very high potential. That is called as second Wien effect. So this effect is actually the Wien effect. You know, there are two effects. One is Wien effect and another one is Falkenhagen. Just to mention, because Falkenhagen, you can remember it as Falkenhagen effect is for changes in frequency of the current. Wien effect is for the changes in the potential of the current. So this effect is called as Wien effect, the potential change. Even though this is a simple question, better to go through the concepts, otherwise you will make mistakes.